of our three different distance measures for computing the distance between two words. And what we saw was that the first two of these measures, edit distance and weighted edit distance, are used for spelling correction in two ways. The first way is to take the query, define a threshold edit distance, say 2, enumerate all strings that are at an edit distance of less than or equal to 2 from the query, look up which of those enumerated alternatives are found in the dictionary, take the uh, take the intersection of that particular set of alternatives with the terms in the dictionary, and then look at the edit distance as well as look at the value of the edit distance as well as the collection frequency to figure out which is the closest word to the query, closest and most likely spelling suggestion for that particular query. The other alternative using these edit distance measures was to take the query term and compute the edit distance to every single term in the dictionary, and then choose the terms with the smallest edit distance and look at their collection frequencies and sort them according to decreasing order of the collection frequency. Now both these alternatives were very expensive because we had to do a large number of edit distance calculations. In the first case, we had to do a large number of calculations or transformations to generate the alternatives, and in the second solution we had to do a large number of edit distance computations to compute the distance between the query and every term in the dictionary. Now what we're going to do is we are going to see how the Jaccard coefficient, which is the third distance measure, can be used for spelling correction in a way that is pretty fast. We don't have to run the dynamic programming algorithm to compute to compute the Jaccard coefficient between a particular query term and a particular dictionary term, assuming that we have a k-gram index already generated. So let's see how we compute the Jaccard coefficient from a given query term to all the terms in the dictionary. So let's work here with a bigram index. Okay, so this is a portion of the bigram index. There are 3 dictionary terms in the bigram index. Note that this bigram index is different from the standard inverted index. Now let's look at a query term called Lord. There are 3 bigrams in it, LO, OR and RD. And what I've shown here is the postings list for those 3 bigrams, LO, OR and RD. The postings list for the bigram LO will contain all the terms that contain the bigram LO. So alone is one, lower is the other, and sloth is the other in this toy example. Obviously there'll be many more in reality. Now suppose I want to compute. So I want to compute all the terms in the dictionary which have 2 matching bigrams with my query term. So recall that the Jaccard coefficient is defined as a ratio, but before we came to the Jaccard coefficient, we looked at an absolute thresholding where we say that if the query term has an overlap of more than, say, 3 trigrams with a term in the dictionary, then it's a good overlap. Let's start with that because the calculation there is going to be more obvious, and we can compute the Jaccard coefficient with a minor tweak of that algorithm. So one of the things that I want you to think about here is one of the things I want you to remember here is how we did a walkthrough, a pointer walkthrough during our intersection operation in chapters 1 and 2. We are going to do a similar walkthrough here, except that instead of 2 pointers, we are going to have 3 simultaneous pointers walking through these 3 postings lists. In fact, even the solution that we discussed in chapter 1 could have been adapted to incorporate more than 2 pointers. We had 2 pointers there when we were taking the intersection of 2 lists. But if you want to take the intersection of 3 lists or 4 lists or 5 lists, we can do them in one shot by using 3 pointers or 4 pointers or 5 pointers. And in each step of that walkthrough, if we add more pointers, then in each step of that walkthrough, we will increment the pointer that is pointing to the smallest doc ID. But here, of course, we don't have doc IDs. We have terms in the standard inverted index that have been sorted in lexicographic order. So again, the postings lists of the bigram index are sorted. And why are they sorted? Precisely to enable this kind of walkthrough. So we are going to have 3 pointers. Okay, I'm going to call them P1, P2, and P3. And the first thing I want you to visualize is forget about what we are doing in order to compute the Jaccard coefficient or to compute whether or not there is a match. Just think about how we're going to do the walkthrough first. We're going to start with the 3 pointers pointing to the first terms of the lists, and in each step we are going to increment the pointer which is pointing to the least term. And by least term I mean the term that appears first in lexicographic order. Okay, so if you look at these 3 terms, alone, border, and ardent, alone is the term that appears first in lexicographic order. If you were to look up a dictionary, you're going to find alone appearing before these 2 terms. So we are going to increment P1 to point to the next term. Now in the second step, we have lower, border, and ardent. Now ardent is the smallest in lexicographic order. So we'll increment P3 to point to the next term, which is border. Now between lower, border, and border, we now have a tie between P2 and P3. Both of these are pointing to the smaller term. Lower is later on in lexicographic order. Now when there is a tie, we are going to increment both the pointers together. Just as when we had a tie between 2 pointers and we were using only 2 pointers for the walkthrough, we would increment both the pointers together. That's what we'll do here also. And if we get a tie between all 3 of them, then we'll increment all 3 of them together. So because there is a tie between P2 and P3, we will increment P2 to point to lower, and we will increment P3 to point to card. Now in the next step, we see that there is a tie between there's no tie actually. We have lower, lower, and card, right? Yeah. So P3 will be incremented to, and it's going to cross over the end of this list, assuming that the list ends here. So P3 is already done. It's reached the end of the list, but we still have P1 and P2 to work with. So there's a tie between P1 and P2, so both will be incremented together. P1 here and P2 will point here. Now between P1 and P2, P2 is pointing to the smaller term, so now P2 is going to reach the end of the list, and then P1 will reach the end of its list. So you see how this pointer walkthrough is done using 3 pointers, right? Now what I'm going to do is I'm going to add a calculation step for every uh, snapshot of this walkthrough. Okay, I hope the walkthrough itself is clear to you. Now in each step, as we are walking these pointers through, we are going to compute the overlap between the query term and the current term in the bigram index that we are examining. Okay, and what is the current term that we are examining? Because in the beginning we have 3 pointers pointing to 3 different terms. So how do we define what is the current term? Well, the current term is simply the term that is least among the 3 in lexicographic order. Okay, it is that particular term which is going to be left behind and moved on from. Okay, so the term that's just going to be left behind, or the term that appears that is smallest in lexicographic order among all the 3 terms, that is going to be the current term. Okay, think of that as the current term. So what is the current term at the beginning? It's alone. What was the current term in step 2? Ardent. What was the current term in step 3? Border. What was the current term in step 4? Card. In step 5, lore. In step 6, morbid, and then sloth. Now notice that if you were to lay down the sequence of these current terms, you would get a sorted sequence of all the terms in this entire postings lists, the set of postings lists here, in alphabetic or lexicographic order. Any questions about this? Now what we're going to do is, in each step of this walkthrough, we are going to compute the overlap between the original query term and the current term that we are examining. So how do we compute the overlap between the query term and, let's say, the first current term? So the first current term was alone. That's the first current term. So what's the overlap between Lord and alone? It's actually 1 bigram. And how do we know it's only 1 bigram? Because there is a single pointer that's pointing to alone. Okay, the other 2 pointers are pointing to words that appear later. Now note that each of these postings lists correspond to 1 bigram in the original query. That means if all 3 pointers are pointing to the same term, okay, in this case, in this example, that case never happens, but we do get a case where there is a term like border or a term like lore, which becomes the current term for 2 pointers simultaneously. That means that this particular current term, when this term becomes current, we can say at that stage that there are 2 bigrams that are common to the query term and this term. Right? When at the beginning we have a single pointer pointing to alone, we can say that there is exactly 1 bigram that overlaps between the query term and this particular term. Because if there was more than 1 bigram overlapping, then there would have been other pointers pointing to this term. So that means this term should have appeared somewhere in this postings list and somewhere in this postings list. And obviously it should have appeared at the very beginning because these lists are sorted. So is that clear? How during this walkthrough we can trivially compute how many diagrams overlap between the query term and the current term. And what we will do is, we'll say that if the number of overlapping diagrams is 2 or more, we are going to append the current term to an answer list. So just like before, we'll have an answer list to which we will append, entries. Earlier we were appending doc IDs to the answer list for creating the result of a search query. Now we are going to append to the answer list terms that have a good overlap with the query term. And these are the good candidates. The terms that are going into the answer list, they are the good candidates. And note that this answer list can be computed in time proportional to the time it takes for this pointer walkthrough. So we just need a single pass through all these 3 postings lists in order to compute this answer list. Any questions about this? So this by itself is a spelling correction algorithm, right? Because for any particular given query term, you can split it into its bigrams. So if there are 4 bigrams in the query, you will do a pointer walkthrough with 4 pointers together. And then you will create this answer list based on whatever threshold you've defined. And the terms that are in the answer list at the end, when all 4 pointers have reached the end, then at that stage, the terms in these answer lists are the terms which have a good overlap with the query term. So you can look at their collection frequencies at that stage and then decide which of those um, lexicon terms or dictionary terms is the best spelling suggestion for that query term. Right? So taken in itself, this procedure is uh, a spelling correction algorithm in itself. Any questions on this? So if there are no questions, yeah, somebody turn on the microphone. Any questions?
No, sir.
Okay. So maybe one of you can tell me how you would adapt this procedure to compute the Jaccard coefficient between the query term and the current term.
Hello.
Yeah.
So when we are going through this walkthrough, so whenever we have a tie at the current term for a value more than the threshold frequency, we would
So,
like increment. So
by the way,
So
we
you-
don't have a threshold on. So when we talk about the Jaccard coefficient, we're not talking about this threshold. Now the threshold will exist for appending a term to the answer list. So let's say,
oh yes.
okay, so let me talk about, so what does a threshold mean here? If the Jaccard coefficient between a query and current term is more than some threshold value, let's say it's more than 0.8, then you will append current term to answer list. Okay, so the thresholding works differently when you talk about Jaccard coefficient. Now obviously you need to compute this first, and so you'll need to first explain how you would compute this during the walkthrough.
Sir, in this case, if there are three lists, would it become X intersection Y intersection Z?
No, remember that we are taking the Jaccard coefficient is defined between a query term and the current term. So we are looking at a bigram index here, right? So
Oh, okay, okay, sir.
what is the definition of Jaccard coefficient? It's the in so x so let x be the set x is going to be the set of bigrams in the query term, and the set y is going to be the set of bigrams in the current term. Okay. Now if you have 3 pointers, that means there are 3 bigrams in the query term.
Yes, sir.
Right? So if you're doing the walkthrough with 5 pointers, that means there are 5 bigrams in the query term. And if there is a tie, okay, if let's say there is a tie between 2 pointers here, that means the number of bigrams in the current term. Okay, one thing you need to note here is you don't need to calculate y separately. Okay, you need to calculate the numerator and the denominator. So first question, how would you calculate x intersection y? What is x intersection y? X intersection y is the bigrams common to the query and the dictionary term. And what would that be?
So like, sir, I mean, depending on the query terms, like, what? I mean, if we.
So let's look at the first term alone. Okay, so there is a single pointer. There are no ties here. How many bigrams are common to the query term and the term alone? One, right? Because alone appears in only one of the three lists. Right? These three lists are the lists corresponding to the bigrams in the query term. And alone appears in only one of the lists. That means alone has only one of the bigrams out of the three in the query term. So you can you can compute the size of the intersection based on how many pointers are tying for the current term. Okay, so let's look at the step where the current term is border. There are 2 pointers, okay, which have a tie at border. That means the term border has 2 out of the 3 bigrams that appear in the query term. So this is the number of pointers that have a tie at the current term.
Okay, sir.
Yeah.
The X union Y would be the number of the total words that we have generated minus the common ones. Say suppose we have two borders, so we could take as one border and we could calculate the number of words that has been generated in the K diagram index.
In the K, okay, the number of bigrams that will be generated by border.
Yeah, in this case it would be 9 minus 2, it will be 7. So we have like
what
alone.
is 9?
So all the words that has been generated here, alone, lower, sloth, border, lower, morbid. So there are all 6 words. So out of that, 6 plus 1, 7, 8. 8 would be the X union Y.
Okay, so let me caution you on one thing. When you're looking at border, don't look at what these other terms are. When you're looking at border, you're trying to calculate the Jaccard coefficient between border and lord, right? So no other words come into the picture here when you're computing the Jaccard coefficient between lord and border. Likewise, when you're computing the Jaccard coefficient between lord and lore, the other words are not, I mean, they're irrelevant, right? Even if they had been present or not present, that's not going to make a difference to the value of the Jaccard coefficient.
Uh, so is it so the like if the union of the bigrams we've generated for Lord
Mhm.
and the union of the bigrams generated for border, like the number of size of that list, that set?
Okay, in set theory, how do you define, like, what's the formula
So
for the set of union?
so
Suppose you
it
are
would
already given the set intersection.
so it'd be size of border plus size of Lord minus size of border intersection Lord.
Yeah. So the size of the union is going to be the sum of the sizes of the two sets minus the size of the intersection. The size of the intersection is something you already know because that's the number of pointers that are tying at that current term. So this is something you know. This is also something you know because this is just the total number of pointers that are part of the walkthrough, right? Because if there are three bigrams, that's why you have three pointers. What is the size of y?
So it would be the length of border.
Hmm.
How many characters are there in that? Then
Hmm.
whatever minus n, whatever the n is, n gram index plus one.
Okay, okay, yeah. So in this case, for a bigram, so the number of bigrams in border, okay,
So
would
with
be
duplicates removed also.
BOR, yeah. So that's true, but as an approximation, you can, as a heuristic, you could take it as with duplicates because, let's say there had been duplicates in the query term, right? So you could have imagined two pointers walking along the same list together, right? You don't want to remove duplicates because if there are bigrams appearing multiple times in a word, right? And if let's take a word like um, and let's take these two query terms. Sorry, this is the query term and this is the dictionary term. Now these two sets are not the same, right? I mean the set of bigrams here, if you remove duplicates, they would be the same. But if you don't remove duplicates, then you can see that they are not the same, right? And I don't know about this, about the startup. So there is a startup called PYAZZZA, Piazza. Okay, so it's a startup that was started by somebody from IIT Kanpur, and um, their product corresponds to some kind of a discussion forum for conducting online courses. So if we could have started a Piazza group for this class, but it's something you can try out. Anyway, my point is, while typing in this particular term, somebody could type in an extra Z by mistake, right? And if you were to remove duplicates, then you know you would not be able to detect the spelling error. Is that clear? So even though I mentioned a set, think of it as a bag rather than as a set. Okay. So think of working with a bag of trigrams rather than a set of trigrams. Okay, what is a bag? A bag is a collection of items where duplicates are allowed. So the answer to this question about what the size of y is actually simple. You can just take it as, in case of a bigram index, it would just be the length of the term minus 1, right? Because BORDER will have the bigrams BO, OR, RD, DE and ER. So the first bigram starts from the first letter of the word and the last bigram starts from the penultimate letter in the word. Right? So the number of bigrams is the number of letters from the first letter to the penultimate letter, which is the length of this string minus 1. So you know what these three values are, and you can compute the Jaccard coefficient on the fly. And if the value of the Jaccard coefficient happens to be more than this threshold, then you will append that term to the answer list. Questions?
So no questions, sir.
Okay. What I just described is a spelling, is an independent spelling correction method, but you can actually think of combining this method with the edit distance method. Remember that the previous method we discussed, where we want to compute the edit distance between the query term and every term in the dictionary, was too expensive. It was too expensive because we have to run the dynamic programming algorithm as many times as the number of terms in the dictionary. But if we use this k-gram index to calculate the how many terms there are in the dictionary that have a good overlap with the query term, if we generate this answer list, then we can follow up this method with a series of edit distance computations between the query term and every term in the answer list. Now these are all good candidates. So the number of edit distance calculations that you'll have to run is going to be small. Okay, you don't have to run the algorithm for every term in the dictionary. You have to run it only for the terms that are in the answer list. And if you define your threshold to be high enough, then the size of the answer list will hopefully be small. Of course, it will be much smaller than the number of terms in the dictionary. And so you can get the best of both approaches here by first running this linear time algorithm, which will generate the answer list of good candidate terms that overlap with the query, and then you can do a more precise edit distance computation to find out which is the most likely spelling suggestion for the query term. So that finishes with isolated word correction.